So today we're going to continue with our topic on differentiation. And before we get started with that, I want to also give you an overview of what we're going to do this semester. Sorry, not this semester, this month, the month of April. So if all goes well, you should be able to see my screen. Make it a bit smaller. So we have a little bit of work to do this week, the week of April the 4th, to talk about differential calculus. So that's going to take this lecture and then also the next. And then for the next 3 weeks onwards, we will do a couple of separate topics, and they're going to be a bit more algebraic in nature. So we'll talk a little bit about complex numbers next week. And then we'll have a few sessions on quadratic expressions and polynomials. So basically looking at polynomial expressions, finding roots, synthetic division of polynomials. You'll see it's a bit more technical, a bit more algebraic, but also quite useful. And then last, we'll finish off this algebraic section with a bit of binomial theorem. So this is a particular application of the theory of polynomials that we will cover in detail when the time comes. And then I want to draw your attention to this section, in particular, proof techniques. This is always something that is considered to be the most difficult or the most complex part of the course. So we'll spend maybe one and a half sections. So it's not a lot of time, but we'll talk a little bit about proving theorems. So up to this point, what we've done is we've constructed nice arguments and they count as proofs in their own rights. But there are some special techniques like proof by contradiction, proof by induction that you can use to build more general proofs. So it's a bit more conceptual, but that's for the last week of April. And then after April, then we're almost at the end of the semester. Then there's a few more weeks, but not too much. And then the remainder of the semester is basically going to be devoted to integral calculus. So also weeks 10, 11, and 12 is going to be all integral calculus. So after we've done differentiation, then we're basically halfway with the course. And then what's left is some algebra and some integral calculus. And then we're already done. That's how quick it goes. I would also like to draw your attention to the next quiz. So we'll have another quiz number 2. And that's going to take place on either the 19th or the 21st of April, depending on what session you are in. So it's going to be part of week 8. And the topics will be announced later, but we'll cover coordinate geometry for sure, limits and continuity, and maybe a little bit of differentiation, but we'll communicate closer to the final date. Okay, so with that, let's resume where we left off. Differential calculus. So we talked about the motivation for computing derivatives, which was derivatives give us slopes to functions. So if we want to compute a slope, then we end up computing this particular limit that you see on the bottom of the page, and that limit is actually an example of a derivative. This is what at the end of last time we called the derivative of the function f at a point A, so f prime of A. And then we did one example. We calculated one derivative by hand. So we took this polynomial function and then we wrote out the entire definition of the limit. We simplified here and we took the limit to obtain whatever this number is. And the last message at the end of, at the end of last section, we talked about how cumbersome that is, like you have to do quite a lot of manipulations, but there's actually rules that will let you calculate this derivative in one go. And that's what we're going to do today. So we need a little bit more of definitions, but just to set the scene. And then the bulk of today is going to be establishing those rules. And on the exam, on the quiz, and so on, you can just use the rules. You don't have to always write out the derivative, the limits. In fact, nobody does that unless it's a new function that you don't know. But if you can use the rules, use the rules. So in terms of a bit more things to cover for us, we can talk about the derivative as a function. So in order to set the stage for that, let me begin again with the definition of the derivative f prime. So we know that that is given by this expression for the limit. So the limit of f of x plus h minus f of x, and then we divide that by h. And all I've done here in writing down this expression is I've changed the variable. So on the previous slide, this was called a, and now I've called that x, and here I have an x, and here I have an x as well. And what does that buy me? So this was the derivative. But if I write it like that, then you see that the derivative itself, you can see that as a function of x. And this is something that's going to be very useful for us as a slight change in perspective. So rather than computing the derivative at a single point, f prime of a, now we're not going to fill in the a with a number. We're just going to say compute the derivative for an arbitrary value x. And what you get is a result that's going to depend on x. So it's a function of x. And maybe let's do an example to see what I mean by that. But before we do that, let me also introduce a little bit more of notation. So if we have y equal to f of x, so we have a function f of x, and we call that y, then we'll use the following notations for derivative. So we'll use f prime of x. We've already seen that notation. We'll use df dx. And this makes it explicit that we're taking the derivative with respect to x. And we'll also, if we focus on this y, we'll also write this as y prime of x, or even just y prime, or dy dx. So all of these notations are used interchangeably, and they all mean the derivative. Okay. And implicit in all of those is the fact that, yeah, what we have is a function of x. So let's see how that plays out in an example. So let's take the function f of x equal to the square root of x. And here, remember, x needs to be positive or 0 in order for us to take the derivative. But we will assume that x is positive to make it just a little bit simple. So let's calculate the derivative, and let's use our limit formula for that. So f of x is limit as h goes to 0 of square root of x plus h minus square root of x divided by h. That's just the formula that I had up here. That's formula star. And now we can calculate that limit. So what we'll do is we'll multiply by the conjugate. It's always a good idea to multiply by the conjugate if you have a limit that involves square roots. because otherwise it's very difficult to deal with the square roots. And now we'll work that out. So we get x plus h minus x for the numerator and h square root of x plus h plus the square root of x for the denominator. And now the x here and here cancel. And we're left with limit h going to 0, h divided by h, x plus h, x, like so. Now we have another cancellation, the h here and the h here cancel. And we have limit of h going to 0, 1 over square root of x plus h plus square root of x. And now I can let h go to 0 in this last expression, and I get 1 divided by 2 times square root of x. And so to summarize, this tells us that the derivative of the square root function is 1 divided by 2 times the square root function itself. And here you see really nicely that the derivative is itself a function of x, because you see on the right-hand side you have that x. So depending on what value you substitute for x, the result is going to change. So here very clearly we see that the derivative is a function of x. Okay, so now one other subtlety that I want to address before we make our hands dirty and do some calculations. And that's a little bit the fact that I said here, well, let's take x to be greater than 0. Why did I have to do that? Well, it is because everywhere in this calculation, I take a limit. And if I want to take that limit, I have to make sure that I can take the right limit and the left limit and compare them. Because remember, that's what we have to do if we compute a limit. We have to make sure the left limit and the right limit are the same. And so now if we, and I'll squeeze it in over here, if we put x is equal to 0, then if we want to calculate the derivative, then we can use the same prescription divided by h. But now I have to be very careful if I take that limit for h going to 0, because I cannot take the limit from the negative side. I cannot say, oh, sorry, and here I should substitute x is equal to 0. So I get h and then square root of 0. So if I let h go to 0 from the negative side, then I'm in trouble because I have that square root of h and I can't take a square root of a negative number. So in this case, the left limit, the limit as h goes to 0 from the negative side does not exist. I can only take the limit from the positive side. And that's a bit of a problem, because if we apply our definition really strictly, that means that the derivative of the square root does not exist for x is equal to 0. And that's maybe a bit too strict. We want to be able to say, I have a derivative at x equal to 0, and it is given by a certain value. Or, well, maybe it's not defined at 0, but I want to be able to talk about the derivative at a certain point. I don't want to have to say, well, the limit doesn't exist, so therefore it doesn't make sense. And in order to address that, we can talk about the left and the right derivative. And before we get to that, let me introduce one other piece of vocabulary. So when we have a function, f of x, and we compute the derivative f prime of x, then we say that f prime is differentiable If we say that f, the function f is differentiable, if the derivative exists for all the points in the domain or for all the points in a certain set that you may be interested in. So differentiable means the derivative exists. So for example, I think we already calculated, or you can calculate this example pretty easily yourself. So if we take, for instance, x squared, then the derivative is 2 times x, and this is differentiable. So f of x, f prime of x is 2 times x. That expression exists for every value of x. So here we say f of x is differentiable for all x in the set of real numbers. And in particular, what can happen is that we have a function that is defined on an interval. So we know square root of x is defined on the interval 0 to plus infinity. And now we want to know, is it differentiable in that interval? So we've already established f prime of x is 1/2 square root of x for x bigger than 0. So we know it's differentiable for all x greater than 0. But now, what about x is 0? At the previous slide, we left it off saying, like, right now we can't say anything about x is 0 because the limit doesn't even exist there. So can't even say anything about the derivative. And in order to resolve the question now, I was hoping this wouldn't happen. Let me just move that slightly. Give me a second to move that text a bit around. It will be a bit nicer to look at that. This falls under, I should prepare my Blackboard before doing the class, but with PowerPoint, it's all a bit more complicated. But there we go, that should be better. And now I can share my screen again. And you should have a beautifully unencumbered view. Oops. Not of my application, please. Of my presentation. Okay, you should be able to see the same thing as before, except it's not overlapping anymore. So what do we do when we have, for instance, a function that's defined on an interval, and we want to say something about the bounds of that interval? Because we already know, hey, the limit may not exist on the bounds of the interval. In that case, what we can introduce is the right derivative at the leftmost bound of the interval and the left derivative at the right bound of the interval. So we have our function like this, defined on an interval a, b, and we sort of want to say something about the slope at b and the slope at a. So in order to find out what the derivative, what the slope is at a and b, we'll talk about the right derivative on the left end and the left derivative at the right end. It's switched. Why is it switched? Because the terminology for right and left comes from the limit that you have to take. So here, for the right derivative, we'll take a right limit. So h going to 0 plus. So we will walk towards a from the right side, and we'll look at what happens to the slope if we approach a from the right side. And then conversely, for b, we'll take a left limit. So here we will walk towards b from the left side, and we'll look at what happens to the slope. And so in that way, what you end up getting is you have two expressions for the derivative at either end of the interval. And they basically tell you what is the limit of the slope if I approach a from the right, or if I approach b from the left. Okay. So with that in mind, we can answer the question that we had for the square root. Sorry, my pen color all of a sudden stopped responding. I will have to do it manually. Okay. So what do we have for the square root function? So here we have an interval with a bound 0. So let's look at the right derivative at x is equal to 0 of the square root function. And then what you'll see by virtue of the definition that, or by the calculation that we did on the previous slide, that derivative is f prime of 0, limit h going to 0 from the positive side, square root of h minus square root of 0 divided by h. And if you simplify, and I won't write it down because I don't have space, you have square root of h in the numerator and an h in the denominator. So you get a 1 over square root of h in the denominator. And if you let h go to 0 here from the positive side, you will end up with plus infinity. And so in this case, we have to say that the slope becomes horizontal, becomes vertical in that point. The slope is infinity, or it's not a number, it doesn't exist. So that's just a small addendum, and it fits with what you already know about left and right limits or left and right continuity, where you have a function on an interval which may not be defined outside of the interval, but you still want to say something about what happens at the end points of the interval. And then we have maybe one other example that I can briefly mention because it's an interesting one. So here we'll look at f of x is absolute value of x. And so we know that that's a function that has two different prescriptions based on whether x is positive or negative. So when x is positive or 0, the absolute value is just x. And when x is negative, then the absolute value is minus x. And we can also draw that function. This is a very important graph to keep in mind. It's this V shape that meets at a right angle here in the origin. So this is y equal to absolute value of x. So now we want to know, where is it differentiable? And we can do two things. We can look at the figure, and let's do that first. So the figure tells me what is the slope of this line. Well, if I look at negative x's, I see here that the slope is -1. And if I look at positive values of x here, I see that the slope is +1. And now the big question is, of course, well, what is the slope of this function at the origin? And I think you'll agree with me that here this slope does not exist. So the function sort of goes down, and then all of a sudden at the origin, it flips by 90 degrees and goes up again. So at the origin, we can already see the slope does not exist. So this leads us to believe that, hey, if I look at the figure, I think this function is going to be differentiable everywhere. So it has a slope everywhere except at x is equal to 0. And okay, that's our intuition from the figure. Now let's calculate that. So let's compute the derivative. And we'll look at a number of different cases. So first, we'll look at what happens when x is positive. So if x is positive, the derivative is given by the limit for h going to 0 of absolute value of x plus h minus absolute value of x divided by h. And now there's a few things that we know. Well, first of all, we have that absolute value of x is equal to x since x is positive. And secondly, we can also say something about the absolute value of x plus h. So x is positive, and h, I don't know too much about h, but the one thing that I know about h is that I'm going to make h smaller and smaller, because that's what I have to do when I take a limit, make it smaller and smaller and see what happens. So from that, what I can basically conclude is that x plus h is also going to be positive. Because, so the absolute value is going to be x plus h, since x plus h is positive for small values of h. So if x is 1, let's say, we want to compute the derivative at 1, then of course, if h is -2, x plus h is -1, that's negative. But if I make my h small enough, let's say 0.1 or 0.01, x plus h or x minus h is going to stay positive. So that's an important point, because now we can get rid of those nasty absolute values, and we can just write this limit as x plus h minus x divided by h. And of course, the h cancels, and we have limit of h going to 0, h divided by h. So that is, of course, 1. So that tells us that our slope is 1 for all positive x's. And now you can do the same thing for negative x's. So it's the same computation. And I'll let you do it yourself. And you should find that this is equal to -1. And then the last thing that you can do is you can look at x is equal to 0. And there what you'll find is that the left derivative is equal to -1, because you come from the negative side, and the right derivative is going to be equal to +1. And those two are not equal to one another, of course. So it's not, so the derivative does not exist. at exist at x is 0. And then backs up your intuition that, yeah, it's differentiable anywhere for positive numbers, for negative numbers, except at x is equal to 0. There, the derivative doesn't exist. So now, with that in mind, we have a couple of interesting properties that link differentiable and continuous functions. And one of them is, if you have a function that's differentiable, then that function is automatically continuous. And I have written the precise statement on the slide, but it's worth thinking a little bit what that means in plain English. So what does differentiable mean? Differentiable means the slope exists. And what does continuous means? Continuous means the function does not have any jumps. And the statement that I'm making on this slide says that if the slope exists, then that means the function does not have any jumps. And if you think about it, or if you make a small figure for yourself, that makes sense, because for the slope to exist, what that means is the function has to be varying gradually. It can sort of have a corner or a 90-degree angle like the absolute value function. It has to vary gradually. And of course, if it varies gradually, then it cannot have any jumps. So, of course, that's the intuition, but now let's make it a bit more concrete. Let's see if we can prove that. So let's start with a function f of x that is differentiable at x is equal to a. And what we want to show is we want to show that it's also continuous at x is equal to a, as it says on the slide. So if we write that out a bit more, we want to show that the limit for x going to a of f of x is f of a, because that's what it means to be continuous at x is equal to a. And so in order to do that, let's look at the following limit. Let's take the limit x going to a of f of x minus f of a, and see if we can do something. And one thing that we can do is we can write this as f of x minus f of a again. And now we're going to divide this piece by x minus a. And then in order to keep the limit the same, we have to also multiply by x minus a. And this is a nice thing to do because this thing now looks like a derivative. And that's great because we know something about the function in terms of its derivative. We know that the derivative exists. So let's play with that a little bit and see if that gives us anything. So one thing that we can do is we have a limit of something times something else. Let's write it as the product of two limits. Times limit x going to a, x minus a. And now we're almost there. I'm just going to continue over here. And let's look a little bit at what we've isolated in those two terms. So the first term here, you recognize the derivative f prime of a. That's just the definition of the derivative. On the other side, what we have here is the limit of x minus a as x goes to a. That's a very simple limit, that is just 0. So basically what we end up with is f prime of a times 0. And now you're going to say, that's 0, right? I'm multiplying something with 0, so the result is always 0. Not so fast. That is true if the thing that you're multiplying with is a number. But are we sure that f prime of a is a number? That is not always true. Think, for instance, about the square root function, where we said, hey, at 0, the derivative is infinite. If the derivative is infinite, then infinite times 0, that's undefined. We can't draw any conclusions about it. So here, we would very much like this expression to evaluate to 0. But for that, we need the derivative itself to be a number, not plus or minus infinity. Thankfully, that is going to be the case because we know that our function is differentiable. So if we write it in a different way, we know that f prime of a exists and is equal to a number. So then here we can say, yep, that product is 0. Because again, f prime of a exists. That's the differentiability assumption. And so now what does all of that buy us? Well, we have that the limit of f of x minus f of a is equal to 0. And what does that tell us about the limit of f of x itself? Well, we can write this as the limit of f of, and now I need to be a bit careful, so f of a plus f of x minus f of a. And I'm going to put the brackets here so that you see where I'm trying to go with this. So I haven't changed anything. I've just written f of x as f of a plus f of x minus f of a. But now I can write this as the limit of f of a plus the limit of f of x minus f of a. And well, what do I know? Well, limit of f of a, that's just a function value, that's a constant, that's f of a. And limit of f of x minus f of a, that's what I've shown already here. That is equal to 0. So here I get f of a plus 0 or just f of a. And now, what do I have at the end of the day? Well, I have I started up with the limit of f of x as x goes to a, and I ended up with f of a. And that is precisely what I needed to show in order to conclude that my function is continuous. So from that, I can conclude that, yes, my function is continuous at a. So again, slope exists implies does not have any jumps. Differentiability implies continuity. Just want to make one quick remark about that. So the converse does not hold. You have to be a bit careful. So the function absolute value of x is continuous at x equals 0, but not differentiable. We just proved that. So differentiability is stronger than continuity. Differentiability implies continuity, but continuity does not imply differentiability. So then just before we dive into our calculations, one further piece of notation or one further concept, that of higher order derivatives. So if we have a function f of x, let's say x squared, then we can compute its derivative, f prime of x. And I think we've already calculated, or you can check it yourself or wait one slide. You can calculate its derivative, it's going to be 2x. That is a function of x itself. So we can again take a derivative. We can differentiate that again, derivative. And then we get what we call the second order derivative, which we denote by f double prime of x. And that is going to be equal to 2. So this is the second order derivative. And by the same token, sometimes we call this the first order derivative, or just the derivative. If you don't say what order it is, it usually means it's the derivative. And we can keep doing this. We can take the third order derivative by differentiating the second order derivative one more time. And the second order derivative is a constant, so the derivative of that is just 0. So this is the third order derivative. And we could keep doing that, but once you have something at 0, if you differentiate again, you stay at 0. You keep having 0. And so the notation that I wanted to show is precisely what I've shown on the slide. So the number of primes, the number of ticks, indicates the order of the derivative. But there's also a slightly different notation, or a bunch of notations actually. So we will denote f prime, f double prime, f triple prime for first, second, third order. But that gets a little bit verbose. If you have, let's say, the seventh order derivative, you don't want to have to put 7 ticks. So what we usually do is we write f and then n between parentheses for the nth order derivative. With n large. So typically n 4, 5, and so on. So that is one piece of notation. The other notation that is used quite a lot is the dy dx kind of notation. So we'll also write dn of f dxn. That also denotes the nth order derivative. So to make it a bit more explicit, so using the example that we had before, x squared, we can write the second order derivative 2 primes, but we can also write this as d2f dx squared. That's exactly the same thing, and that is equal to 2. And then likewise, f triple prime x is d3f dx3, and that is 0. The reason why there's 2 notations is basically because calculus was invented by 2 people separately in Germany and in England, Leibniz and Newton. They had their own notation. and this was in the time before the internet. So by the time they found out that they each had invented calculus, they already had their own group of school of people working with them, and they couldn't change it without upsetting a lot of people. So historical oddity, two different notations, but both are useful. I would say I like, just to riff on this a bit, I like the notation with the primes if it's clear what I'm taking the derivative of, or like if I need some notation that's very condensed. And I like this notation if I want to be explicit, to say, hey, I'm taking the derivative of the function f with respect to the variable x. So different notations, different use cases, more or less. So with that in mind, it's finally time to dive into some useful rules, and we'll build this up little by little. We'll start by establishing a rule for the derivative of a polynomial. And in order to get there, we'll establish two even simpler rules. We'll first prove that the derivative of a constant is always equal to 0. And the derivative of x to a power n, where n is a natural number, is equal to that number times x to the power n minus 1. So 1 minus, so the number minus 1. And that rule is true when what am I trying to say here? When n is different from 0. That's not entirely correct, is it? No, I think that's right. I will come back to that. So okay, I'm a bit confused, but let's work through the proof, and then we'll see it coming up if I've made a mistake or not. So let's start with the derivative of a constant, and let's do this nice and slow. Let's write out the definition. So I have to take the limit, and now I have to take the function value at x plus h, but the function is everywhere constant, so that's c, and then minus the function value at x, so that's c again, and then divide that by 0 and take the limit. And so, of course, you see what happens. I have 0 in the denominator divided by h, so that's the limit of 0 divided by h. That just gives me 0. So my first rule is very easy to prove in just a simple calculation. And now for the second rule, we have to do a bit more work. So let's write this out in long and in full. So I'm going to have to take the limit as h goes to 0 of the function at x plus h, so x plus h to the power n, minus x to the power n, and then divide all of that by h. And now it gets a little bit complicated, but not too much. don't worry. I have this power n, and I really want to get that h out of that power, because then I can say something about the limit as well. And if this n was a number, then I could just calculate x squared, x cubed, I can just calculate. But I want to do this for arbitrary n, so I don't have the right tools at my disposal. What I'm going to do is I'm going to show you what this term looks like if I write it out in full. So if I take x plus h to the power n, and if I work that out, then the first thing that I'm going to get is x to the power n. And then the next term is going to be n times x to the power n minus 1 times h. And then I'm going to get another term with a coefficient that I'm not going to tell you about. So there's a number here that I'm purposely keeping hidden. And then I get x to the n minus 2 h squared. And then I get another coefficient, x to the n minus 3, h to the third. And that pattern continues. So you see the powers of n dropping until finally I have no more x's left. And at the same time, you see the power of h increasing, h squared, h to the power 3. And the last term that I'm going to get is h to the power n. So all of these symbols, they're unknown coefficients. They're unknown, and it turns out they will be unimportant for what we're going to do here. And if you say, hey, I really want to know what those coefficients are, don't worry. In about 3 weeks from now, we will see exactly what they are, because this is going to be a special case of the binomial formula, or the binomial table. So just bear with me for a second. Okay, so with that in mind, let's calculate what our limit works out to be. So we get limit h going to 0. And now we substitute this whole thing, x to the n times x to the n minus 1 h. And then I'm just going to write one more term, little square, xn squared h squared plus dot 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 plus h to the n. So that's x plus h to the power n. And now I still have to subtract minus x to the power n. And all of this I have to divide by h. And now, okay, we can simplify. We have x to the power n here. We have x to the power n there. They both cancel out. And there's another interesting thing that we can observe if you look at the remaining terms. Here we have an h. We have an h squared here. All of these terms that I haven't written down, they're going to be h to the power 3, h to the power 4, and so on. So let me just highlight the h. But they all will have an h up to and including the h to the power n. So what I can do is I can factor out one h and write the limit as follows. Limit h going to 0, h times n to the power x minus 1 plus, and then that little square, whatever that is, x to the power n minus 2 times h plus dot 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 plus h n minus 1. And now all of that divided by h. And now you see the next calculation that we can do, the cancellation, so the h here and here cancel. And we're left with the terms between parentheses. And now again, look at where the h's appear. So there's an h here, there's going to be h's here, and there's an h here. And that's important. But here, there's going to be no h. So let's take advantage of that and write our limit as limit h going to 0 of the first term, that's x n times x to the power n minus 1, and then plus limit h going to 0 of all the rest, so all the terms with the h's. And in order to make that a bit more clear what's going on, I'm going to factor out that h. So I'm going to write this as h times square x minus 1 plus dot 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 plus h to the power n minus 2. So what I've done is I've taken that highlighted h and I factored it out here. And now there's two things that we can do with that result. So the first term here, n times x to the n minus 1, doesn't have any h's. So if we let h go to 0, we just get n times x to the power n minus 1. And then the second term, this big limit, here we have an h up front, and then a bunch of other terms which may or may not have h's in it. But if I let h go to 0, then what's going to happen is everything in between parentheses is going to go to 0 because we multiply it by h. So this whole big messy limit here is going to be equal to 0. And we're left with just n times x to the power n minus 1. And that gives us precisely our second formula right here. And if you track to the reasoning, you can also see why this has to be for n different from 0, because if n is equal to 0, then again you have x to the power n, that's 1. And if you take the derivative of that, that's 0. So that rule does not apply for n equal to 0. Okay. These two rules are very important. You should know them by heart, because if not, you will have constant trouble calculating things with derivatives. So now let's move to our goal of computing the derivative of a polynomial. There's two more rules that we can deduce. I'm not going to go through all of the details, but basically the next rule up says, if we have a function that's multiplied by a constant, then we can take out that constant out of the derivative, and the derivative is just c times the derivative of the original function. And then likewise, if we have the derivative of a sum of functions, f plus g, then that's the same thing as taking the sum of the derivative, so df dx plus dg dx. And the same thing is true for the difference, f minus g. If you take the derivative, that's derivative of f minus derivative of g. We can maybe prove one rule, and I will let you do the other one yourself if you're not convinced. So let's compute ddx of c times f of x by the limit definition, h going to 0. So that's c times f x plus h minus c times f of x divided by h. And now you see, of course, you can factor out the c here and here and take that out of the limit to get limit of fx plus h minus fx divided by h. So that is c times the derivative of f. And now for f plus g, you can do the same thing, but I will ask you to check this yourself. It's same level of difficulty. And now what we can do is we can calculate the derivative of an arbitrary polynomial with those 4 rules. So let's take the polynomial where we calculated the derivative way back in the beginning with the limit. So that was 3x squared plus 7x minus 5, and derivative of all of that. So I'm going to write it out in long and in full to say what rules we use. So first, let's use rule number 4, the one that says that the derivative of the sum is the sum of the derivatives, to chop this up into monomials. So write this as ddx 3x squared ddx 7x minus ddx 5. And now what we can do is we can take the constant term out of each term. So this is by rule number 3. 3 times ddx x squared plus 7 times ddx x minus 5 times ddx 1. I'm making it ridiculously overcomplicated, but just to be consistent here. Okay, and now we have ddx of x cubed, x squared, ddx of x d dx of 1, or you could write this as x to the 0. Well, it's not, otherwise we'll run into a rule. And so now we do by our rule number 2. We're going to use our rule number 2 and our rule number 1. So let's write it out first here. So d dx of x squared, that's 2x. d dx of x, that's 1. And d dx of a constant, that is just 0. So this is by rule number 2, also by rule number 2, and this is by rule number 1. And then if we put it all together, we get 3 times 2x plus 7 times x, plus 7 minus 5 times 0. And that is, of course, 6 times x plus 7. And if you have never done this calculation before, I would just encourage you to play with this a little bit. And pretty soon you'll do this in one step without writing down all the intermediate steps. You'll just say 3x squared, derivative is 6x, 7x, derivative is 7, minus 5, derivative is 0. So the result is 6x plus 7. So those are the fundamental rules for polynomials. There's a few more rules to cover, but we will not do all of them in detail. So the next 2 concern the derivative of the exponential function and the derivative of the natural logarithm. So here it's a little bit more tricky to derive this from first principles, but basically the derivative of the exponential function is the exponential function again, and the derivative of the natural logarithm is 1 over x. And if you were to write this out, you would see that this is a little bit difficult to prove. So if we, for instance, look at the exponential function, we could write the definition, and you don't have to write this down because it's not going to lead to somewhere. I just want to show you what's involved in proving this. So if you write out the definition, you can write this as follows, divided by h, and then factor out limit. So factor out e to the x, you get e to the h minus 1 divided by h. This term right here does not depend on h, so you can take it out of the limit. And you're left with the limit of e to the h minus 1 divided by h. And now the difficult part, the thing that we're going to skip, is that this limit is actually equal to 1. And the whole expression for the derivative therefore becomes e to the x. For the natural logarithm, you can do something similar, but you'll run into trouble. Also, there's something there that you cannot calculate with what we've seen, so you can just accept this as given. And then there's a slight variation, so let's call this 6b, 6a, and 6b. If you have a logarithm to a different base, then the derivative of a logarithm other than the natural logarithm is again 1 over x, but then times the logarithm, the natural logarithm of the base. And in order to prove that, that's maybe not so difficult. That is something that we can do. So this is 5, 6a and 6b. So let's prove 6b, taking 6a as a given. So for the logarithm to a different base, we can write that as a function of the natural logarithm. That's the natural logarithm divided by the logarithm of a. So that's the definition of logarithm to the base a. And now we take the derivative of both sides, and we get d dx logarithm base a of x is d dx natural logarithm divided by natural logarithm of a. You can write it as 1 over the logarithm of a, d dx of ln of x. And this we've just seen as given, this is equal to 1 over x. So this whole thing becomes 1 over x times ln of a, natural logarithm of a. And then two more rules that are very powerful concern the derivative of a product and a quotient. So you multiply two functions or you divide two functions by one another. What you get out? Well, the rules are given here. They already start looking a bit more nasty, but if you practice with them a lot, you'll see that they're actually quite natural and they'll become second nature. So you should also know them by heart and know to apply them because they're very fundamental. So it's called as rule 7 and 8. We will not prove them. The proof is not so difficult. It's just a lot of calculations, but we will do a couple of examples. So let's start with the derivative of a product. And let's take the derivative of x times e to the power x. And for that, we're going to use our rule number 7. So let's have a closer look. So here we're comparing two things. We have terms in f, and we have terms in g. So here is g, g, g. And if you look at the right-hand side, you see that we first take the derivative of f and we multiply it by g, and then we do plus f multiplied by the derivative of g. So we take the derivative of one term in the product, and we do that twice so that we get a derivative of f and a derivative of g. So let's apply that. So if I use the same colors, x is going to play the role of f, and then e to the power x is going to play the role of g. And then what we get for the worked out solution is we first take the derivative of f, the blue thing, times the yellow thing, that's our g, plus the blue thing times the derivative of the yellow thing, that's dt. Underline it. Derivative of the blue thing times the yellow thing, blue thing times the derivative of the yellow thing. And now, of course, we have to work that out. Well, d dx, the derivative of x, that's just 1 times e to the x. And then the derivative of e to the x, we've just seen that's e to the x. So we get x times e to the x. And I can factor out e to the x and write this as e to the x times x plus 1. And now an example of the quotient rule. So let's compute d dx of e to the x divided by square root of x. And for this, you have to remember that the derivative of the square root function is 1 over 2 times the square root. And actually, there's an important note that I have to make about it. But let's first let's first finish this example. So here, what do we have if we again use the same color? So now f is here. So for the expression, for the derivative, we get a complicated fraction, and we get derivative of f times g, the function that you have in the denominator, and then minus, so that minus sign is important, don't forget the minus sign, and then you get the derivative of g times f, and the whole thing you divide by g squared. So let's apply that. I'm going to write down a big fraction. I get d dx of the function on top, so e to the x times x minus d dx, my square root of x minus d dx of square root of x times e to the power x, and then divided by square root of x squared. And now I can start simplifying that. Derivative of the exponential, that's the exponential again, times square root of x, minus 1 over 2 times square root of x, that's what I already had, e to the power x, and then square root x squared, that's normally that would be absolute value of x, because let me take that back. That's just x, because if we take the square root of a positive number and we square it again, then we get that number back. And now we can simplify that just a little bit to factor out, for instance, the e to the x and bring everything on a common denominator to get e to the x, x minus 1/2 divided by x to the power 3/2. And so the important thing that I want to point out, and I will go back a few slides for that, is take another look here at this expression. If we write this as d dx to the power 1/2, so we take that square root and we write it as x to the power 1/2, then what we have is we have a special rule, we have a special case of our power rule, rule number 2 that we saw earlier. So this is actually equal to n times x to the power n minus 1, with n equal to 1/2. Because if you substitute those values, what you have, well, n is 1/2, is 1/2 times x to the power 1/2 minus 1. So that's 1/2 x to the minus 1/2, so that is equal to 1 over 2 times the square root of x if you fill it. So what I'm trying to show you here is that the rule that we've seen before, d dx of x to the power n is equal to n times x to the n minus 1, as long as n is different from 0. This is valid for arbitrary constants n. And in particular, not just integers. So the small caveat that I want to add here, and then I'll go back to my original slide, is this n here, n can be arbitrary. So it can be a natural number, it can be an integer, it can be a real number, and so on. As long as it's not 0, this rule applies. So for instance, if I do d dx of x to the power pi, what is that? Well, okay, it's just pi times x to the pi minus 1. Okay. So with that, we're at time. There's a little bit more to do that we will cover next time. I just want to give you a sneak preview. So what we still have to do is we have to look at derivatives of trigonometric functions. And then we'll also look at an important rule called the chain rule to derive compositions of functions. So I will stop sharing my screen here. That's it for today. I don't know where you are with your background in derivatives. If you've already covered derivatives in high school, this is probably very basic, but we'll move to some applications pretty soon. If you have never covered this before and you want to know more, or if it all is a bit fast, then do let me know and I can provide additional resources based on what we taught in previous years. So with that, thank you for attending again, and I hope to see you on Wednesday for the next installment of the class. Bye everybody, and have a good end of your day.